Okay, well, we are going to take a virtual field trip today to take a look at the geology of Ontario. It is unfortunate that we couldn't get out today because it is such a beautiful sunny day, and the snow has pretty much disappeared, so we would have been able to see lots of beautiful things. Um, Nonetheless, you get to see me in my home office and a virtual geology of Ontario. So those of you who've just joined, if you could mute your microphones, please, that would be great. Thanks. So there are 4 stops on the field trip today. And the purpose of the field trip is so that you can become familiar with the geology of Southern Ontario. We're also going to take a look at regional stratigraphy. And what I want you all to think about as we move through this and after we're completed, when you're answering the questions, is some of the processes that led to the formation of the geology that we see today. So we have 4 stops. Our first stop is down here at Gannon's Narrows, where we'll be looking at some sedimentary geology. And then we have 3 stops on County Road 36 between Buckhorn and Burley Falls. So we're actually going to start our field trip looking at the youngest rocks of the sequence, or certainly the youngest rocks that we will see today. And then we'll move down stratigraphy to the Great Unconformity, and we will finish up in the Canadian Shield. So let's get started. This is a geological map of the Southern Ontario area. And if we think of this from a stratigraphic perspective, essentially our study area represents about 1 billion years of geological development, just a little bit over. These pink rocks or orange rocks that you see up here in the northern part of the map sheet is the Canadian Shield. So that is the part of the Canadian Shield called the Central Metasedimentary Belt. And these are actually the youngest rocks in the Canadian Shield. Primarily what we're looking at here is a sequence of marble, amphibolite, which is metamorphosed seafloor basalt, and some deformed sedimentary rocks, including things like metaconglomerates that have been intruded by some granitoid plutons. Now, this central metasedimentary belt was formed between 1.3 and 1 billion years ago as part of the Grenville orogeny. So that was a mountain building episode where a period of subduction accreted or scraped off some oceanic crust onto the eastern side of the southern province of the Canadian Shield. Tectonically, what we're looking at is a setting that is similar to the modern Indonesian island arc. And basically, there was a collision of a couple of chunks of continental crust and the formation of a mountain range that was around about the size of the Himalayas at the time. If we take a look at this little map here on the left-hand side, you can see the geology of Laurentia. So Laurentia was the supercontinent that ultimately became North America. And you can see that there are many, many, many different parts to the Canadian Shield. So we are looking here at the red piece, which is the Grenville province. Whoever just joined the meeting, could you please turn your microphone off? So by about 800 million years ago, the Grenville Mountains had essentially eroded away to the shape that we see today, which is a gently undulating low relief plain. We discussed that on our last field trip. It is called a penny plain. And by about 460 million years ago, during the Middle Ordovician period, modern day Canada was actually located in the tropics. So we were sitting somewhere nice and warm. We were much, much closer to the equator, and the Canadian Shield became submerged in a warm tropical ocean. So in that warm tropical ocean, there was a sequence of carbonate-rich sedimentary rocks that were deposited, and those are delineated in this map here in various shades of green. So we're going to be up in this area here, looking at the Shadow Lake and Gull River rocks. We'll also see some of the Verulam Formation. We're not going to see any of the Kirkfield and Coboconk Formation today. So this little map on the left here shows the location of the Paleozoic continents during the Ordovician. Canada was part of Laurentia here. So you can see that we were actually located in the southern hemisphere at the time. There was the Iapetus Ocean here, which was warm and shallow. And this continent over here, Baltica, formed sort of the other side of the ocean. So let's head to Gannon's Narrows. If you're following along with the KML file posted on D2L, could everybody turn their microphones off, please? Could you all mute your microphones? If you're following along on Google Earth, you can click into Stop 1, Gannon's Narrows, and you can drop the little person down onto the road, and you can actually have a look at the location here. So this is an outcrop of Verulam Formation, and this is the youngest material that we'll see on the field trip. It was deposited during the Ordovician, and what we're looking at is an outcrop of thin-bedded, interbedded limestone and shale. You can see that the scale along the bottom there is 1.8 meters. And so we're looking at something that is about 4 meters high. And the thickness of those beds there are fairly thin. The limestone beds, which are the thicker ones, so this is a limestone bed here, is between 5 and 15 centimeters. And the little interbeds that are composed of shale are much, much thinner. They are between about 2 and 5 centimeters thick. So what we're looking at is a fairly strongly weathered outcrop that has a nicely developed zone of talus at the base. So talus is material that has weathered off the slope and accumulated as a set of loose material at the base of the slope. These shale layers, which are a little difficult to see in here, are extremely friable. So that means that they break down very easily. If we were at the outcrop, we could pick up a chunk of it and we could essentially break the shale layers apart. This is because they contain a lot of clay. Shale is primarily composed of silt and clay minerals. And one of the functions of clay, or one of the behaviors, is that it absorbs water and it will swell. So if the shale gets wet, the clay minerals will expand, and when they dry out, they contract. And so that process of expansion and contraction and expansion and contraction is called slaking. And that's a mechanical or physical weathering process where earth materials, in this case shale, disintegrates in the presence of moisture. Now I want you to take a look at this image here. I don't want you to answer any questions right now, but I want you to think about other physical weathering processes that moisture might facilitate in this particular area. And there are also some other physical and chemical weathering processes that are taking place at this particular location. So think about those as you're answering the questions that I will post up on D2L. Does anybody have any questions that they want to post into the chat box? If you have anything that you would like clarified here, before we move on to the next section. And if you have any questions, just put them into the chat box. The chat will get saved for the public messages. Now, can everybody hear me? Okay, good. All right. So in this particular outcrop here, there are some intersecting joint sets. You can see that there is a set here. There is another set over here. And you can see a parallel set here. And these are caused by isostatic rebound. So at the end of the Pleistocene Ice Age, about 10,000 years ago, once the ice started melting, the crust relaxed. It had been compressed from the weight of the ice, which was extremely heavy. There was about 3 kilometers of ice sitting over us in this area here, which compressed the crust and pushed it down into the mantle. As that ice disappeared, the crust was able to rise back up again. It was kind of able to relax, and so these joint sets formed. So primarily, what we're looking at is joint sets that formed from the process of isostatic rebound. Now, neotectonic forces, which I also mentioned in here, these are modern day tectonic forces that are being exerted on the crust from the west coast of North America. So on the Vancouver side of the country, there is a subduction zone. And although it is several thousand kilometers away, the force of that subduction actually translates all the way through the crust, and we see some fractures here. One of the really neat things about this particular outcrop is that there are a lot of fossils. Now, this was deposited during the Ordovician, which was a time when marine invertebrates just exploded onto the scene. So there is a very diverse flora and fauna that formed during the Ordovician, and it was captured in the sedimentary rocks that were formed during that period. If we could go and pick up some rocks, what we would see are brachiopods, crinoids, and bryozoans. So this little image here on the left is crinoids. Crinoids are actually some kind of quasi-plant animal combination that look like tulips. So this is a stem. It's a segmented stem that grew on the base of the sediments. And it was kind of a plant that floated up into the ocean. Bryozoans, these are bryozoan fragments here. And in this image here, we see brachiopods, which are shellfish that look a little bit like butterflies. This image here, F, is just a cross-section through a crinoid stem. So the segmented stems. Okay, anybody have any questions about Gannon's Narrows or the Verulam Formation before we move on? Nope. Okay. So this is stop number 2, which is at the intersection of Deer Bay Reach Road and County Road 36. So this is just to the north of Buckhorn. What we're looking at here is an outcrop of Gull River Formation, and it looks extremely different to what we saw at the Verulam Formation. There are a couple of things that you will notice here. Certainly, there doesn't appear to be the shaly interbeds that we saw at the first outcrop. This is an outcrop here of reasonably thin-bedded limestone, and then we have a much thicker, more pale-colored unit at the base. But we don't see that clastic sedimentation in conjunction with the formation of the limestone. So this outcrop here is approximately 3 meters high, and we're looking at a light gray, thick-bedded limestone overlain by a darker gray, more thinly bedded limestone unit. If you're following along with the Google Earth file, this is location number 2. So this darker gray unit that sits on the top here is pretty interesting. There are a number of fossils in it. It's got some bryozoans, it's got some brachiopods, it's got some crinoids in it. There's also some coral. So there are some rugosid corals in there, which are pretty cool. But it also contains some angular quartz-grained quartz clasts. So it also has a clastic sedimentary component to it, but it does not contain the shale. The lower unit is finer grained. It is much, much more thickly bedded. Doesn't really contain much in the way of fossils, so not super interesting. But one of the neat things about this particular location is that the limestone layers dip towards the road slightly. It's a little bit difficult to see in this image, but if you're following along with the Google Earth file, you can actually move that around and you can take a look and see how it is that the layers are dipping. Now, there is no deformation that has taken place here. So they've not been subjected to stress and they have not undergone strain. Their attitude reflects their original deposition. So I want you to think about what caused that and how that actually corresponds with the law of original horizontality rather than contradicting it. So the questions that are in this story map here are going to be in the D2L little quiz that I will be posting up later today. So just consider some of those things. Okay. Any questions about outcrop number 2? Brad has a message in there. I think I have some of the stem fossils from Finland. That's pretty cool. That's the crinoids. Awesome. Okay. If there are no questions here, let's move on to stop number 3, which is the Great Unconformity. So again, this is on County Road 36, north of Buckhorn. We're a little bit closer to Burley Falls now, so we're sort of moving to the north and the east. And what we're looking at here is the lowermost formation in the Paleozoic sedimentary sequence. So this is the Shadow Lake Formation. We also, in this location, get to see the unconformity between the Canadian Shield rocks and the sedimentary rocks that overlie it. So the Shadow Lake Formation is pretty interesting. It is the base of the sedimentary sequence, and it is the oldest rocks that we see. And what it represents is a near-shore depositional environment. These reddish-colored rocks along the base of the image here are arcosic sandstones and conglomerates. You did see some of these in the lab. I've also included a photograph here on the left of arcosic sandstone. You can see that it's very coarse-grained and it contains a lot of pink minerals. So I want you to think about what that pink mineral actually is and where it might have come from. Overlying that reddish material, you see some argillaceous limestone and thin-bedded shale. So argillaceous limestone just means muddy limestone. Argillite is clay, mud, clay, silt. So it is a silty, clay-rich limestone and some thin-bedded shale, and that all comprises the Shadow Lake Formation. Now, if we take a look at this this next image here, you can see that we've got the Shadow Lake Formation with the arkose and the limestone, but we have a contact here, which I have drawn in red, between the sedimentary rocks and the underlying Canadian Shield. Now, what that unconformity represents is about 500 million years of lost geological information. So to the right of this red line here, we have got Canadian Shield material, And what we're looking at here in this area with the blue lines is steeply dipping, very strongly foliated gneiss. We could measure a strike and dip off of that. We could measure a foliation. And essentially what we're seeing here is a fabric in the rock that represents northwest southeast directed compression. And that's consistent with the formation of the Grenville orogeny. We have this contact here with the overlying material. And the reason that I say that there is about 500 million years of lost geological information is because the Canadian Shield had weathered away to the peneplain by about 900 million years ago. And it migrated south to the equator. It became submerged in a warm tropical sea. And then about 460 million years ago, the sedimentary rocks were deposited over the top of it. So from about 900 to about 460 million years, either nothing happened or there is no geologic record. So what that red line in the image actually represents is an erosional surface. And this particular type of erosional surface is a non-conformity. So non-conformities are specific unconformities where sedimentary rocks overlie the igneous or the metamorphic rocks. Now, if you want to have a look at a bit more information about unconformities, you can take a look at page 335 in chapter 16 of your textbook, or read the geological time presentation that's posted on D2L. If we were to look at this gneiss in the field here, what we would see is that it is extremely heavily weathered, and it is quite friable. So it's very crumbly. It breaks down super easily. The biotite shows some preferential weathering. And we see some preferential weathering along the foliation because of the differentiation in the different types of minerals. So one of the things that I would like you to think about is when that weathering actually took place. And that will be a question in your D2L quiz. So this is what the gneiss looks like. You've seen gneiss in the classroom before, but essentially what we're looking at is a banded rock that is primarily composed of orthoclase felspar, biotite, quartz, and maybe some plagiate clays. So that is what we're seeing in this area here. Now in this image, we can also see that the sedimentary rocks are draped over the Canadian Shield. So if you take a look at the field sketch that I've posted here on the left, it is essentially a sketch of the view of the photograph that you're seeing on the right there. You can see that there are some steeply dipping foliation planes in the heavily weathered gneiss that have a strike and dip of 38 degrees, dipping 30 degrees southeast. And then we have this nonconformity here, and then we have the sedimentary rocks that are draped over the top of the Canadian Shield rocks. So that gives you a little bit of a clue as to why we see dipping sedimentary rocks that are undeformed. Okay, does anybody have any questions about this particular location? No? Okay. So let's move to stop number 4. If you're following along in the Google Earth file, just click on stop number 4 and you can fly there and you can take a look at the outcrop. So this particular outcrop here is at the intersection of County Road 36 and Highway 28, just outside of Burleigh Falls. And this is our last stop. So this is an outcrop of the Canadian Shield, which is the oldest bedrock in the study area. Now this is the basement rock for the region, so this underlies everything else. You can see in this image that the rocks are strongly foliated, and again, they reflect the northwest-oriented subduction of the Grenville orogeny. There are a couple of different types of rock that we're looking at here. This dark green material with kind of a rusty oxidation on it is amphibolite. And this is metamorphosed oceanic crust. So this used to be basalt. You can see the foliation plains here that have weathered. So these flat surfaces here are actually foliation plains. There are some granitic intrusions. These pink rocks here are granite sills, and they are primarily composed of coarse-grained orthoclase. So the orthoclase is what gives them the pink color. These are a little bit younger than the amphibolites. They intruded late in the Grenville orogeny, and they also show some evidence of folding. If you take a look at some of these little thinner intrusions here, you can see that they are folded. Now, when we look at these and describe their attitude, we describe them as sills. If you take a look at the image on the left here, you'll see that sills appear to be horizontal, and anything that has a vertical attitude is a dike. The reason that these are sills, even though they appear to be vertical, is because the rock has intruded parallel to the foliation planes. So the intrusion is actually conformable with foliation. Now, if you look at this diagram on the left here, you can see that in this case, the sill is conformable with bedding and the dike cross-cuts it. So essentially what we're looking at here is material that has been completely overturned, and from an attitude or an orientation perspective, we would consider this to be a sill because it is conformable with foliation and doesn't cross-cut it. Now, the reason that it intrudes through those planes of foliation is because those zones of weakness. It's much easier for that igneous intrusion to kind of squeeze up through those planes of weakness than it is to try and bust through a solid rock and make its own way through. If we take a look at this from a structural perspective, we see that they are strongly foliated, and any primary structure that might have been evident in these rocks has been completely destroyed. So this is material that was deposited on the ocean floor. We could potentially have seen basalt pillows. We might have seen some layering of the lava flows. That has been completely obliterated by the foliation and by the compressional stress that was imposed from subduction. We also, from a structural perspective, see some jointing. And so there are a number of different joint sets here. There is an almost horizontal set, which I outlined here in red dots. And you can see that there is a parallel set below. And there is a set of vertical joints here. And you can see this joint face here that is being pointed out by the red arrow. And you can see a parallel set here. Parallel joints are considered to be single sets. So this is one set, and then these horizontal joints are another set as well. Okay. So this is normally a 4-hour field trip. We whip through it in about 30 minutes. I see there's a question here from Brad. Would the granite have intruded after the attitude change or before? It would have intruded during. So compression is going on. The whole area is getting squeezed up, and then sort of late in that period of orogenesis, those igneous intrusions are making their way up. So the foliation would already have been there, and the cells would have got pushed to their final attitude as part of the process. But the amphibolite would have been foliated first, and then the cells, and then there would have been some continued sort of late in the orogenesis event that eventually led them to the attitude that they are in. Okay, so I'm going to post some questions for you on D2L. They're mostly done. They'll be up this afternoon. I know this was a pretty brief introduction. Unfortunately, we're somewhat limited, but at least we got to see some fun pictures. This is last year's group at the outcrop. You can see it was a pretty nice day last year. But essentially, what we've looked at is about 1 billion years of geological history. So this field trip is posted on D2L. The Geology of Ontario is also posted on D2L. I'm going to post another PowerPoint up there for you on the geological development of North America, and there will be a little quiz. So I'm going to wrap up the recording here, and then we can have a bit of an opportunity for a discussion or a Q&A if anybody's interested. Okay, thanks, and I hope you enjoyed our speedy little field trip today.